Let's take a dive. The light rapidly fades as we descend past 200 meters and enter the deep ocean, a largely unexplored and little-known world. Once thought featureless and barren, we now know that the deep seafloor is rich with life. Just like on land, our seafloor is characterized by geomorphology, with deep-sea mountains, hills, valleys, and canyons, and these features host amazing biodiversity and vibrant ecosystems. Over the last century, we've visually explored a tiny fraction of the 330 million square kilometers of the deep sea floor. In total, we've seen an area about the size of Rhode Island. But what we have explored has revealed incredible organisms and ecosystems, and new worlds hidden within our own. Our visual exploration of the deep sea floor has uncovered never-before-seen species, 90% of which are new to science. We found evidence of unique adaptations for the extreme light, pressure, and temperature conditions of the deep, and we've been able to identify key pieces of global ocean and climate processes. Learning about the deep ocean and seafloor through visual observation, that is, seeing these environments in images or video footage, is critical for increasing our understanding of our ocean and planet. Seafloor observation is so valuable, so why haven't we done more of it? Why stop at Rhode Island? The short answer is that it's not cheap to dive deep. Specialized vehicles, equipment, and sensors are needed to observe and document the deep seafloor, and the cost of this equipment increases with depth. Furthermore, equipment like the submersibles that you see on the right is typically deployed from a vessel at sea, and this increases the cost of exploration further at a rate of up to $100,000 a day. Historically, only a fraction of nations have had access to these resources and the technology and infrastructure required to pursue deep seafloor exploration. And as shown by the darkest blue countries on this map, these tend to be in the global north. Analyzing metadata, that's the basic records of exploration activity, from the last 100 years of visual seafloor observation, gives us insight into who observed what and where. It points us to the major players and reveals patterns of exploration priorities and locations. As part of my capstone, I sourced these metadata for submersible dives, seafloor camera tows, and fixed camera stations on the seafloor. The datasets came from a combination of federal organizations, private exploration groups, and international research groups and publications. And together, these datasets totaled about 50,000 individual sites. On this map, each site is represented by a tiny yellow dot on the map. A geographic analysis of these metadata showed that 78% of the seafloor exploration activities in our record were within countries' 200-mile exclusive economic zone. This is outlined in white on the map. And 92% of these activities within these zones were in areas controlled by only 5 countries. Looking at the depth profiles of observations showed that 2/3 of sites were on seafloor shallower than 2,000 meters, despite the fact that 80% of our seafloor is deeper than 2,000 meters. And finally, past seafloor observation over-investigated relatively rare geomorphology, like submarine canyons and rifts, thanks James Cameron, while under-investigating more common features like deep-sea plateaus and escarpments. These patterns strongly suggest that current seafloor exploration is not representative and that we're missing the bigger seafloor picture. The places we explore don't reflect the full range of global areas, depths, and seafloor geomorphology, and the focus on coastal regions of mostly the global north also fails to reflect the goals and priorities of all nations with interest in our deep ocean. And so, the goal of my capstone work this year was to facilitate representative observation through a sampling design that balances seafloor depth, geomorphology, and geographic regions, and to facilitate representative participation in seafloor exploration through a planning tool that can capture diverse and shifting priorities across different stakeholders. So how can we plan to observe the seafloor in ways that reflect the global range of its environments? Or put another way, if we could plan the next 10,000 dives, where should they be? To answer this question, I used geographic information system tools and data that covered the entire global ocean. These included our record of past seafloor observations, depth regions from satellite bathymetry, and maps of seafloor geomorphology. And I used these information layers to create a space that lets us prioritize geographic spread and mirror the global distribution of depth zones and geomorphology in choosing new spots on the seafloor to explore. And the results of this analysis looked like this. The yellow points on the map represent those 50,000 seafloor sites that have already been observed. And these new light blue points are our 10,000 new locations. Zooming in a little, you can see that these new locations are spread out across the total ocean area and not just clustered around the coast. Our set of new sites are not only spread more evenly across the globe, but they also better reflect global seafloor characteristics. The depths represented by these new sites, which are the dark blue bars in this graph, mirror the global distribution of actual seafloor depth zones, which are the light blue bars. We also get much closer to matching seafloor geomorphology by area, the light shaded bars, with our number of proposed sites, those darker bars, for a whole range of different features. Overall, these 10,000 proposed new sites more closely represent the depth, geomorphology, and geographic spread of our global deep seafloor. However, when we consider global plans for future exploration, we're visually confronted by the fact that many of our proposed locations lie closest to areas with low deep sea research presence, those with coastal areas on the map marked in yellow, orange, and red. Global capacity needs are complex and diverse, and this map reflects a snapshot of deep sea exploration presence based on a global assessment released by the Ocean Discovery League last year. The proximity of proposed seafloor sites to areas of low presence really underscores the need to build greater global baseline capacity and to specifically develop presence in regions and communities that have historically been left out of deep sea research. How can we facilitate representative participation in global seafloor exploration? In 2022, the Ocean Discovery League released the results of their deep sea capacity assessment, which provided a multifaceted picture of deep sea research interest and technical and human capacity for 186 geographical areas. This included key access metrics for resources like infrastructure, funding, data, expertise, deep sea technology, and vessels. They found that areas surveyed in the assessment varied widely in both their stakeholder interest and capacity for deep sea research. Different areas had unique combinations of deep sea priorities, expertise, and capacity, and resource access needs. This capacity demands flexible, stakeholder-driven strategies for seafloor exploration that are responsive to area-specific priorities. And my goal was to embrace this need for flexible strategies for specifically the case of seafloor exploration, to help stakeholders figure out where the best locations for seafloor observation might be, given their area-specific goals and constraints. To do this, I developed a dynamic web-based planning tool that allows users to adjust the importance of different considerations, like depth ranges, coastal proximity, and vessel traffic, based on their priorities and any constraints they have. The tool uses these considerations to generate a heat map of regions that fit these priorities. And this is very much a prototype at this point, but I'm excited to walk you through this function and see what everyone thinks. The Seafloor Observation Scenario Exploration Tool, as my classmates call it, SOSET, starts with a series of information layers that stakeholders can choose to use or ignore based on their goals. Currently, these include proximity to coastal exclusive economic zones, geomorphology features, seafloor depth zones, previous seafloor exploration activity, and global vessel traffic routes. Once you've chosen which information layers you want to use, you can adjust how important each is based on your priorities by assigning it a specific percent value. For example, if you are limited by depth-specific technology, you may want to make the seafloor depth layer, which I've outlined in yellow here, more important than other layers. You can also adjust the ways in which specific depth ranges are important to your planning. For example, if you have access to depth-constrained tools or technology, you can use the sliders here to place more weight on certain depth ranges by sliding to higher numbers, and less weight on others by sliding to lower numbers. And when you run the tool, it reflects the priorities you've chosen across the entire global ocean. And you're able to zoom into your area of interest and draw a custom shape around it, as shown here. This user-defined area is then summarized in a pie chart that gives the percent of seafloor in that area with different levels of suitability, given your priorities. And within this pie chart, for example, over 34% of the area is medium-high to highly suitable, reflected in shades of orange in the chart and on the map. And in this way, users get an immediate snapshot of their regions of interest and how they line up with seafloor exploration priorities. There's a wealth of knowledge waiting for us on the seafloor, but the difficulty and cost of observation necessitates efficient planning and global participation. Prioritizing representation in both what we explore and who gets to explore it is key to accelerating our global understanding of the deep ocean. And with that, I'd like to acknowledge all of the amazing people I've been able to work with this year, especially my committee members, Drs. Katie Croft-Bell, Judy Gobin, and our own Dr. Greg Rouse. Special thanks also goes to Brian Kennedy of the Ocean Discovery League, Amy Work, our GIS librarian here, and Keith Van Grafflin of Esri Oceans, as well as a host of generous communities of support that I've been lucky to find myself in this year. I'm fortunate to be able to continue this work with funding from the Edna Bailey Sussman Fund. And finally, I'd like to thank my family, friends, and classmates for supporting my work and my decision to go back to school for what I'm sure they hope will be the last time. Thank you so much.
I'm really curious to hear who are the 5 major countries on the higher end, and also a second half of this question is, what kind of inequities did you see as far as like the lack of access to be able to do deep sea exploration?
Yeah, thank you so much. Both very important bookends to this. So on the overrepresented in exploration side of things, we have, of course, countries like the United States, a lot of Western European countries, France, Germany, the UK, with additional presence, especially within their own controlled waters and in countries like Australia and New Zealand as well. And what we really failed to see when we got data from all of these different power players was exploration activity that focused on waters beyond their national interests. So, and that might include, you know, for example, US-controlled island territories, things like that. On the other side, I love your question, and I would also love to direct you to the Ocean Discovery League's global deep sea capacity assessment for this, but the inequities can be summed up in one word: funding. But they really break down into capacity building opportunities to train people in new methods and new technology, access to key data structures and processing to be able to use whatever exploration data they're able to collect, and of course, access to those very expensive vessels and deep sea submersibles and other technology. And so these problems all go hand in hand with, I think, efforts to build deep and cheap technology, as it's called, that can be deployed in new ways. This is one of the things that I'm interested in using vessel traffic routes. So if you can leverage existing vessel traffic and you have access to things that are not multi-million-dollar submarines, can you accelerate your country's observation and exploration of deeper waters? But yeah, if you connect with me, I'll send you those reports.
And Kristen, we just have time for one more question, but who do you see using this tool?
I love that question. I've been very lucky to be able to talk with a lot of different possible users of this, and there are two use cases that I'm really excited about. One is with the Crustal Ocean Biosphere Research Accelerator Group, which is a mouthful. COBRA is the easy acronym. And this is a group that trains future expedition leaders to explore the ocean. And I've been talking with them the past couple of months about whether or not this tool could be a really great training opportunity for global exploration and expedition planning, and whether we can make these considerations a little more top of mind for the future of international exploration planning. And the other is, of course, this might strike some people in the audience as essentially a marine spatial planning tool. And with the imminent biodiversity for areas beyond national jurisdiction policy that will hopefully come to pass soon, you can imagine the power of having an almost instant snapshot of parts of the ocean that we don't normally engage in spatial planning around. So those are two use cases I'm super excited about. Thank you, everyone.